So this is the second part of our question. To those who haven't watched the first video, we've calculated the stress in the aluminium tube and in the steel tube due to the force F. So now what we are given another question, which was part B. If in addition to the force F, the assembly is subjected to a temperature change of 20 degrees, find the stress set up in the steel and the aluminium. So that is what we're going to do. So I'm going to read the whole question just in case you didn't see the first question. But in the link below in the description, you can find the link to the first question. I've solved it using two methods, and after that I'm going to solve. A steel tube is fitted around solid aluminium cylinder, and as shown, that was the diagram. The assembly is compressed between rigid plates by central applied forces. So we have these forces F and F. The aluminium cylinder, we're given the diameter of the aluminium cylinder and also given the diameter of the steel. And the question was, if the force F, which is being applied, is 240 kilonewtons, we have to find the stress set up in the steel tube and the aluminium cylinder. So that's what we've calculated, and also calculated the change in length of the assembly. And this was the second question. If in addition to the force, the assembly is subjected to temperature change, I think I've said that, we have to find the stress set up in the steel and in the aluminium. So this type of question, it's now a combined effect. You have to be very careful. It's not a combined effect. Why is it a combined effect? We now have the stress due to the axial force F, and we're going to have the change in stress, and we're going to have the stress due to the temperature change. So that means if we do all this, if we calculate the stress due to the axial force and the stress due to the temperature, we're going to find what we call the resultant stress, and we're going to add, for aluminium, we're going to add the stress of the aluminium due to the axial force, and the stress, we're going to add the stress due to the temperature change. And lucky enough, we've calculated the stress due to axial force. That's what we did in the last video. So now what we're going to do, we're just going to calculate the stress due to the temperature, and after that we're going to add them together. So the stress due to the axial force, as you can see, these forces were compressing. So the stress in aluminium was 58.4 megapascal, and the stress in the steel was 19.46 megapascal. So now let's calculate the stress due to the temperature, and after that we're going to add them together. But since we're in mechanics, you have to take note of the signs. That's why I've written negative here to indicate that it was compressing, because in temperature change you're going to see it's going to be the opposite, because if something is heated, it will expand. Okay, so let's get to the question. So before we do anything, you have to make sure that we have listed all the data that we have. So we're given the force, we're also given the diameter, I've said it. So what I did in the last video, I calculated the area, and the area is here, area of the steel and area of the aluminium. We're also given the modulus of aluminium, modulus of steel, and the thermal coefficient. We're given thermal coefficient of steel and aluminium. We're also given a temperature change, which is 20 degrees Celsius. And now, since I've said I've calculated the stress due to the axial force, we know that the stress is 58.4 megapascal, and due to the stress of the aluminium, 19.46 megapascal. And remember, it was compressive force, so that's going to be negative. So now what we're going to do, I'm going to calculate the stress due to the temperature. Okay, so what is going to happen here? This is more of like a superposition. We've calculated the stress due to the force, so now we don't need that force. We're now concerned about the temperature. So what we have is we have our metal, we have the steel, and we have the aluminium. So the reason why I've just drawn the steel here and not on the bottom, it's just a tube. The steel surrounds the aluminium, so you can just say this is the portion of the steel and this is the portion of the aluminium. But many people make a mistake. Some may treat this as individual bars. That's when you see someone saying we have 2s plus 1a. No, that's going to be wrong. Okay, so what is going to happen here? I'm going to use the stiffness method. So I'm going to follow all the stages that we're going to have. So let's explain what is going to happen. So this is going to be our assembly before anything happens. But the moment that we're going to increase the temperature, we know there's going to be a metal which is going to increase faster than the other one. And in this case, from our thermal coefficient, we're given the thermal coefficient of steel and the thermal coefficient of aluminium. That means aluminium is 23, and for steel is 12. So the one with the higher thermal coefficient is going to expand more faster and also contract more faster. So it's going to be the thermal coefficient of aluminium is greater than the thermal coefficient of the steel. That means when this thing expands, aluminium is going to expand more. So it's going to expand from here to here, and the steel is going to expand, but it's not going to be longer compared to the aluminium. But in that process, since this thing are rigid, aluminium is going to be put back due to the force being exerted by the steel. And on the other hand, the steel is going to be pulled due to the force which is being exerted by the aluminium. Okay, and there's going to be a compromisation where the length of these two metals will be the same, and that is somewhere here. So what is going to happen? The aluminium is going to expand right here, but it's going to be pulled back, and we have to take note of that. That's why we have written this force. There's going to be a force which is going to pull this back, and there's going to be the force which is going to pull this to the right. So that means during this process, the stress of the steel is going to be positive, and the stress of the aluminium is going to be negative since it's going to be put back. So you have to take note of that. So that means if we calculate the forces, the stresses here, that means we're going to add the force of the aluminium, and we're going to subtract the force of the, we're going to add the force of the steel and subtract the force of the aluminium. Okay, so there are many methods to solve this question, but in this video, I'm going to use the stiffness method. So what we're going to do first is to draw a free body diagram. So the free body diagram, let's draw it. So this is the free body diagram. We're going to have a temperature change right here, and we're going to have Fs, which is the force of the steel, and we're going to have Fa here, and I've told you the reason why. Fa is facing this direction, and Fs is facing that direction, and we have the external force, which is the temperature change. We have forgotten about F because we already calculated the stress due to F. Problem equation, it now depends with which side are you resolving. So in this video, I'm going to take the right as the positive. So I'm going to say all forces that are acting on the x-axis should give me 0, right? So what do I have? You see, Fs is going to be positive. So I'm going to have positive Fs here, but Fa is going to be negative minus Fa, and that should give me 0. So we're going to say here Fs equals to Fa. And the next thing that we're going to do, we know we have Fs and Fa, and we can call this equation number 1. So we're going to need another additional equation, and that is going to be the equation of compatibility. So what we're going to do, I'm going to choose Fs, the force, which is the force exerted by the steel, and Fa, the force exerted by the aluminium, as redundant. That means I'm going to ignore them for the meantime. So I'm going to write here Fs, and so since it's another stage, let me just put a line. Fs and Fa are redundant. Okay, so I'm going to apply an external force, and that external force is the temperature change. It's going to be the force or the change in length. So temperature change is the external force. So I'm going to write the displacement relation of this force, the force displacement relation of the temperature change. The force displacement relation of the steel is going to be the change in length of the steel. So I'm going to write Es due to the temperature. That is going to be, what is it going to be? It's going to be thermal coefficient of the steel times the length of the steel times the temperature change. And you can call this equation number 2. And we're going to have the change in length of the aluminium due to the temperature, thermal expansion of aluminium, length of aluminium. We're going to have the change in temperature, and it's going to be third equation. Okay, and now we're going to put the redundance back, and I'm going to find the force displacement relation due to them. Okay, so let's start by the force displacement relation of Fs. So I'm going to write the change in length of the steel. It's going to be Fs, as you can see, it's going in this direction. That's why I've written it as a positive, times the length of the steel divided by the area of the steel and the modulus of elasticity of the steel. So that's going to be the fourth equation. And the length, the change in length of the aluminium is going to be, look, the aluminium is going to be put back. So it's going to be negative Fa, length of the aluminium times the area of the aluminium times the modulus of elasticity of the aluminium. That's going to be the fifth equation. So I think we have 2 unknowns and 5 equations. I think that is, you can appreciate that these questions are enough to solve this problem. So here I'm going to write the equation of compatibility, that the steel and the aluminium, this cylinder, this assembly is fixed. So that means the change in length of the steel should be equal to the change in length of the aluminium. So this is the equation of compatibility. Total change of steel. So I'm going to write the total here. It's going to be the change due to temperature plus the change due to the force Fs, and the total change of aluminium. It's going to be the total change of aluminium due to temperature times the total change of aluminium due to the force Fa. Okay, And since the total change should be the same from the compatibility equation, and remember, while resolving, going this direction, taking the right as the positive. Now let's write it. So the change due to temperature of the steel, alpha S, Ls, and the change in temperature, plus, since said that the steel is going to increase in length, what's going to be put back? It's going to be put by the FA force, by the cylinder, by the force due to the aluminium. So I'm going to add, and I'm going to add the displacement, which is right here, which is going to be Fs, Ls, As, Es. And this, so I'm going to equate this to the change in length due to temperature of the aluminium. And we say the temperature is going to pull the aluminium right here. So it's going to be positive. I'm going to write alpha A, La, change in temperature. And since the force, the result says Fa is going to pull now. It's going to pull the aluminium back due to the force being exerted by the steel. So it's going to be negative now. So since we're adding, I'm going to write plus here, but it said it's negative, so it's going to be minus Fa, La, Aa, Ea. And I think from here you can see the length. The length is going to be the length of the La. It's going to be the length of the cylinder. And you know La is going to be equal to Ls is going to be equal to L. And nothing can stop us from dividing both sides by that length. Okay? And the other thing, but before I mention that, let me just group this. I'm going to put the temperature terms on the right hand side and all the terms on the left hand side. So I'm going to have Fs, As, Es plus Fa, Aa, and I'm going to have Ea, and this should be equal to alpha A, change in temperature, alpha S, change in temperature. And from equation 1, I think everyone remembers equation 1, we know that Fs should be equal to Fa. That was equation 1. So that means you can sub 1 into this. So if we do that, we're going to make Fs or Fa. Let me start by Fs. So it's going to be Fs, As, Es. And we're going to have Fs, Aa, Ea. That should give us, let's just factor out the change in temperature. We're going to have alpha A minus alpha S right here. Okay, and you can factor out Fs here. And if you factor out Fs, what are you going to have? Going to have 1 over As, Es plus 1 over Aa, Ea. So the subscript A means aluminium and S steel. We're going to have the change in temperature, alpha A minus alpha S. Okay, and I think now it's time to divide both sides by this. We're going to have change in temperature. We're going to have alpha A minus alpha S divided by 1 over As, Es plus 1 over Aa, Ea. Okay? And it's time to plug in our values. We have everything that we need right here. Okay? The temperature change is 20 degrees. Alpha A is 23 and alpha S is 12. I'm going to factor out 10 to the power negative 6. In this case, I'm not going to put the units, but you have to put the units. But to save space, I'm not going to put the units. And I'm going to divide this by 1 over, what is going to be S? It's going to be the area of the steel, which is 900 pi millimeter squared, but we're going to deal with meters, so I'm going to multiply that by 10 to the power negative 6 times the modulus of elasticity, which is going to be, ES is 210 giga. Giga means 10 to the power 9 plus 1 over area is going to be 1225 pi times 10 to the power negative 6. That's going to be area for aluminium times the modulus of elasticity of aluminium, that is going to be 70 times 10 to the power 9. And if we solve here, we're going to get Fs as 40.77 kilonewtons, right? And you know that Fs is equal to Fa from 1, and it's going to be 40.77 kilonewtons. We now have these two forces, and it's time to calculate stresses. The stress of the steel due to temperature is going to be, the force is going to be 40.77 kilonewtons. When divided by the area, which is going to be 900 pi times 10 to the power negative 6 meters. And if we do that, we're going to get 14.42 megapascal. The stress due to the temperature. And now let's go to stress of aluminium due to temperature. It's going to be 40.77 kilonewtons divided by the area is going to be 1225 pi times 10 to the power negative 6 meters, and that is going to be 10.6 megapascals. Okay, so we have this. Now it's time to calculate the resultant stress. So we want to find the stress of the whole assembly. We have the stress due to the force and the stress due to the temperature. We're going to write it here. Resultant stress. So the resultant stress of the steel is going to be, so first you said the steel resultant was negative 58.4 megapascal due to the compression, and this is going to be an increase, so we're going to add it 14.42 megapascals, and we're going to get negative 43.98 megapascals. And the stress of the aluminium, initially it was negative 19.46 megapascals. We're going to add 10.6 megapascals. Okay, since I said that the aluminium is going to be acting on the opposite side, it's going to be put back, so that is going to be negative here. So it's going to be negative right here. And I'm going to add the two together, and I'm going to get 30.06 megapascals. So I can write our stress here. There's no need to put negative or positive right here since you know the resultant. So the stress of the steel is 43.98 megapascals. Stress of the aluminium, I've written steel here instead of aluminium, it's going to be 30.06 megapascals. So thank you for watching. Don't forget to subscribe.